when church towers did more than just ring bells. The skyline of the 19th century looked familiar, yet it carried functions we no longer recognize today. If you walk through almost any European or American city built before the year 1900, a curious pattern begins to emerge. Church towers, city halls, observatories, factories, and even hotels often feature metal rods, spires, domes, and conductor networks projecting upward into the air. The explanation commonly given today is simple: lightning protection, according to the standard narrative. These rods appeared after Benjamin Franklin's experiments in the mid-18th century and served only one purpose: to safely guide lightning into the ground. But when historical records are examined more carefully, this explanation turns out to be incomplete. Detailed technical documentation from the 19th century, including patents, architectural plans, municipal maintenance logs, and scientific publications, reveals a more complex and technically sophisticated reality. During the period roughly between 1840 and 1920, auctioneers across Europe and North America actively experimented with what was then called atmospheric electricity or terrestrial electricity. This was not fringe speculation or mystical thinking. It was methodical engineering conducted by trained professionals, published in respected journals, and implemented in real structures that still exist today. The foundational concept behind these experiments was well understood at the time and remains valid today. A measurable electrical potential difference exists between the Earth and the upper atmosphere. The planet's surface carries a net negative charge, while the ionosphere carries a net positive charge. Between them exists a persistent vertical electric field. Under fair weather conditions, this field typically measures between 100 and 150 volts per meter of vertical altitude. At just 10 meters above ground, the potential difference can exceed 1,000 volts. This field is not constant. It varies with weather conditions, geographic location, time of day, and solar activity. Victorian engineers measured these variations carefully using electrometers and galvanometers, recording their results with precision. The question they asked was practical rather than philosophical. Could this naturally existing electrical potential be harnessed for useful work? Patents from the period demonstrate that this question was taken seriously. Engineers designed atmospheric antennas, elevated collectors, roof-mounted conductor networks, and grounding systems with specific materials, dimensions, and installation methods. These were not abstract ideas. They were physical systems built according to detailed specifications, some of which operated commercially for years. Municipal records from several pure European cities mention atmospheric lighting systems installed in public buildings. Technical journals from the late 19th century occasionally report successful demonstrations conducted in front of engineers and scientists. Crucially, many of the structures associated with these systems remain standing today. When one knows what to look for, components of atmospheric collection systems can still be identified within preserved historical architecture. Not all lightning rods were installed solely for protection. Some were part of capture systems. Certain configurations, multiple rods arranged in complex geometries, horizontal conductors extending outward, thick copper cables descending into basements exceed what is necessary for simple lightning protection. They make limited sense as defensive measures, but they make technical sense when understood as components designed to collect long-range direct current from the atmosphere. Why did this technology disappear from public awareness? The answer is not conspiracy, but practicality. As combustion-based electricity generation using steam, water, and later fossil fuels became more reliable, scalable, and predictable, atmospheric systems lost their relevance. Fuel-based generators could operate independently of weather, deliver consistent power, and scale with increasing demand. Atmospheric systems, by contrast, were intermittent and supplementary by nature. As electrification expanded rapidly and The early 20th century, standardized generation methods dominated. Atmospheric capture gradually faded from engineering practice and survived mainly in patent archives and historical publications. This investigation examines physical evidence that still exists today. It explores how these systems functioned based on period documentation. It analyzes why they were viable in the technological context of the 1800s, but could not scale into the modern era. It distinguishes real, documented atmospheric systems from exaggerated and unsubstantiated claims. And it demonstrates that the history of electrical technology is far richer than the simplified narratives often presented today. This is not a story about unlimited free energy or suppressed inventions. It is a story about real, limited, but functional engineering that served specific purposes. Before being replaced by more practical alternatives, consider the architectural evidence. Church towers built between 1850 and 1910 in cities such as Leipzig, Vienna, Boston, and Cincinnati often display elaborate metal configurations at their peaks. Franklin's lightning protection design requires only a single pointed rod connected directly to ground. Yet many towers feature multiple rods, radiating outward horizontal elements forming perimeters, and conductor networks spanning entire rooftops. Architectural documents occasionally reference these installations as atmospheric capture systems, used alongside lightning protection. One documented example is St. Nicholas Church in Leipzig, constructed between 1844 and 1847. Archival records mention electrical experiments partially funded by a local scientific society. Photographs taken before the tower's destruction in 1943 show a complex copper rod arrangement far exceeding protective requirements. Vienna City Hall, built between 1872 and 1883, features metal domes connected by a grid of conductors. Preserved architectural plans label portions of this system as an atmospheric capture network used for emergency lighting. Maintenance logs from the 1890s. Reference capacitor, replacement and insulation testing. Scientific institutions also participated. The Cincinnati Observatory, built in 1873, installed overhead conductor networks around the building. Observatory. Publications from the late 19th century describe measurements of ground potential and atmospheric current. Photographs show an extensive cable system unnecessary for lightning protection alone. Industrial facilities were no exception. A textile factory in Manchester, built in 1881, featured a metal roof. Geometry connected to grounding systems and capacitor. Banks used to stabilize supplementary lighting. Patents filed between 1860 and 1920 provide further confirmation. These documents were registered in official patent offices and include detailed diagrams, material specifications, and operating principles. An American patent granted to Nathan Stubblefield in 1871 describes an apparatus designed to utilize electricity naturally existing between earth and air. British, French, and German patents describe elevated conductors, grounding systems, capacitors, and voltage regulation mechanisms. These patents do not claim extraordinary results. They describe modest power outputs sufficient for charging batteries or operating low-power devices. Scientific journals of the period reinforce this picture. Publications in Philosophical Magazine, the Proceedings of the Royal Society, and the Journal of the Franklin Institute report careful measurements of atmospheric electricity. Authors document microampere scale currents under favorable conditions and openly discuss limitations. Their tone is sober and technical. The presence of these studies in prestigious journals demonstrates that atmospheric electricity was considered a legitimate field of research. Some systems moved beyond experimentation and operated commercially. The Brevoort Hotel in New York installed a rooftop atmospheric collector in the 1890s that supplied supplementary current for emergency lighting. The Blue Hill Observatory near Boston maintained detailed records of atmospheric collector performance. For years, a textile factory in Lyon documented fuel savings achieved through supplementary atmospheric power. A lighthouse in Cornwall used atmospheric collection as a backup system for maintaining batteries. These installations functioned reliably for extended periods before being replaced by grid electricity. To understand why atmospheric systems made sense at the time, it is necessary to consider historical context. Electrical demand in the late 19th century was minimal compared to today. Early incandescent lamps consumed less than 10 watts. Telegraph equipment required milliwatts. Scientific instruments required voltage more than power. In this environment, systems producing tens of watts intermittently were useful. Installing a steam generator was expensive and complex, particularly for isolated buildings. Atmospheric systems offered a quiet, fuel-free supplement. Modern electrical demand renders such systems impractical. The atmospheric electric field is real, but available current density is extremely low. Air is a strong insulator. Even with optimized collectors, practical power outputs remain in the watt range. These limitations are imposed by physics, not by engineering failure. Atmospheric harvesting was not abandoned because it did not work. It was abandoned because it could not meet growing demand. It is essential to distinguish real historical engineering from exaggerated claims. Genuine atmospheric systems are characterized by modest power outputs, detailed documentation, physical evidence, and an absence of sensational language. Exaggerated claims promise unlimited energy, lack technical detail, and rely on conspiracy narratives. Historical records show that serious engineers understood both the possibilities and the limits of atmospheric electricity. The physical evidence remains accessible today. Historic towers still display unusual conductor arrangements. Museums preserve 19th century electrical instruments. Patent archives are publicly searchable. Scientific journals are digitized and available online. Municipal archives retain architectural plans and maintenance records. The evidence is not hidden. It requires careful examination of primary sources. The history of atmospheric electricity illustrates how technologies emerge, serve specific needs, and fade as conditions change. A technology can be real, functional, and well documented, yet still disappear. Forgetting does not imply suppression. It is often the natural result of progress. So, did engineers extract electricity from the air in the 1800s? Yes, in a limited but documented and functional way. Atmospheric capture systems provided supplementary power for specific applications and operated successfully for years. They were replaced not through conspiracy, but through the natural evolution of technology and infrastructure. Understanding this history enriches our view of technological development and reminds us that progress is rarely as simple as the stories we inherit. If this investigation, based on physical evidence and primary documentation, has expanded your understanding of electrical history, support this work by liking the video and subscribing. Turn on notifications to continue exploring forgotten technologies through verified research, not speculation. Thank you for taking the time to examine real history grounded in evidence.